Hi, I'm very glad to present our work and would like to thank you for the opportunity. Transcranial application of FUS to a specific brain area is known to change its excitability with a great future potential for various neurotherapeutics. Among large animal models that can provide translational informations, we chose a sheep due to their cranial and neuroanatomical similarities to humans. Based on our recent study on anesthetized sheep, we found that functional modulatory effects on the motor circuitry were transient and reversible with the existence of optimal sonication parameters. However, as the anesthesia can confound the excitability of neuronal tissue, the modulatory effects from sheep need further interrogation during awake non-anesthetic state. Therefore, we use the sonication parameters identified from our previous work and examines their effect on fully awake sheep. The main hypothesis of the study was that application of FUS can modulate unilateral functional motor circuitry and generate different responses from corresponding leg muscles. To conduct study in awake sheep, we designed wear FUS headgear, which can reproducibly place an acoustic focus on the desired brain location, and investigate the bimodal effects of FUS by detecting electromyography (EMG) from both hind limbs. Functional MRI was performed to identify sheep-specific motor areas. We applied 3 experimental conditions, which were, first, on-target stimulation of primary motor area and the thalamus, second, off-target, and third, no FUS. In the off-target condition, sonication was delivered to the area about 1 centimeter posterolateral to primary motor area. We obtained EMG data from 10 used after training them to wear vest, a FUS headgear, as well as to walk on a treadmill. The FUS headgear was custom-made to fit to each sheep using 3D printing. To position the headgear each sheep in reproducible fashions, we applied 3 tattoo markings on their scalp and obtained MRI data for image guidance. In this fashion, the image guidance could be done without the presence of animals. Prior to FUS experiments, the headgear was aligned with respect to the marking and strapped over the head. We used a single element transducer of focal length of about 3 centimeters operating at 250 kilohertz. We applied separate set of parameters for excitation and suppression as described here. For excitatory sonication session, sheep stayed still while EMG data was obtained. For suppressive sonication, sheep walked on a treadmill for 5 minutes, FUS was delivered for 1 minute after establishing the baseline EMG level. The acquired raw EMG data was filtered, rectified, and temporarily smoothed. The DC signal offset was also removed. None of the animals showed visible movement of hind limb elicited by the sonication. However, the stimulation of M1 and the thalamus selectively yielded group level elevation of EMG signal amplitude from hind limb contralateral to sonication compared to that from ipsilateral side. In suppressive FUS sessions, we found that sonication successfully reduced the EMG tones while the sheep were walking on the treadmill. As you can see from these plots, sonication temporarily reduced the amplitude of contralateral EMG compared to the one from ipsilateral side. We demonstrate the neuromodularity effect it previously reported among anesthetized sheep who were reproduced in awake state. We are currently analyzing rate and time latency of responses to assess the differences between anesthetic and non-anesthetic states. Histological analysis did not reveal any sign of brain tissue damage, and all animal behavior was normal throughout the study. These results attest the safety of the method. We believe the FUS can be safely administered in awake or bimodal, providing translational information for FUS future studies. This study was supported by the NIH grant. I'd like to thank PI Dr. Seung-Sik Yu, and our study staff for their dedication. Thank you.